right, so good morning. Welcome everybody back to our third and last day of the summer school. And so today we have a very exciting program that we're going to get started with. So the first presentation today is going to be Katie Bouman. She is going to tell us about some really exciting work around the interface between machine learning and astronomy. And I really look forward to your talk.
Great, yeah, thanks. Can I use this microphone?
Yes.
Or, okay.
Actually, we can use. Better if you use this one.
Okay.
Sorry.
Should I?
Don't mind. I'm taking over.
Can you hear me okay? Oh, yeah, that sounds, I think good. Great, yeah, so thanks so much for inviting me today. Yeah, so I work in an area called computational imaging, and I'll talk today about moving beyond the first portrait of our Milky Way's black hole by leveraging underlying structure. So this neurosymbolic programming is new to me, but I hope that some of the stuff that I talk about today might inspire some ideas and projects and stuff. So I'd be happy to talk to you all about that later and get your ideas. So, but I'm just gonna first talk a little bit about imaging black holes to begin with, and then talk about how we might move forward with using this kind of underlying structure. So if you go out past the bright city lights, you might be lucky enough just to see a stunning view of the Milky Way galaxy. And if we could travel past millions of stars, 27,000 light years towards the heart of our spiraling Milky Way, we would eventually reach a cluster of stars that's right at the center. And by peering past all the galactic dust with infrared telescopes, astronomers have mapped the past of this cluster of stars over decades. And what they see is really quite remarkable. As the stars come close to the center, they get whipped around by some massive but unseen object that's just sitting there. And by tracking the motions of the stars over time, astronomers have concluded that within the orbits of these stars must be a compact object with a mass equivalent to 4 million of our suns. In fact, this discovery led to the Nobel Prize in Physics given in 2020 for the work of Andrea Ghez and Reinhard Genzel for the discovery of a supermassive compact object at the center of our galaxy. And for many years, people have believed that this compact object is in fact a black hole, an object so dense that its gravitational pull will suck up anything that ventures too close, even light. But at the distance that these stars are orbiting, we can't say for sure. So in order to really study the black hole, we have to zoom in 1,000 times closer. And there, Einstein's theory of general relativity makes some really exciting predictions for what we should see. So light propagating near a black hole doesn't follow straight lines. It's actually curved because the black hole is actually curving space-time. And so photons can even go in complete circles around the black hole. And so if this 4 million solar mass compact object was a black hole, then the space around it would be lit up by this hot gas spinning around, and you have lots of photons flying around. Some of those photons are going to fall into the black hole, but other ones just graze it and are bent by the gravitational pull, such that the net effect is that the black hole basically casts a shadow on a backdrop of hot emission that's almost perfectly circular. But this ring just doesn't take on any size and shape. If Einstein was right about general relativity, then its size and shape would be related to the mass in the spin of the underlying black hole. And so if astronomers were right that this compact object were in fact a black hole of 4 million solar masses, then we should see a ring of 50 microarc seconds across with not a lot of wiggle room. And after many decades of studying this mysterious object, just 2 months ago, we revealed the first image of this massive body, an image that actually perfectly lined up with prior observations and theory. And so this is the very first picture of the black hole at the heart of our own Milky Way galaxy, a radio source called Sagittarius A star, or Sag star for short. And taking this picture, as I'll talk about later, took this Earth-sized telescope and an Earth-sized team. But what makes taking a picture like this so difficult? Well, there's many layers, but the first is that the first fundamental challenge is one of scale. Because the Sagittarius star black hole is so massive, it occupies a size roughly the size of Mercury's orbit around the sun. And that might sound large, but at a distance of 27,000 light years from us, it's like trying to photograph a single grain of sand in New York all the way from where we are and around Los Angeles. And so taking a picture of something that's that small required this international collaboration of scientists from all around the world, building new instruments and algorithms to make it possible. So today, at first, I want to tell you a very abridged story of how we were able to take a picture of a black hole. But at this point, you may be saying to yourself, wait, I'm feeling a lot of deja vu because didn't I hear this story before? And if I turn this image around, it might look like a lot like another image that you may have seen a few years back. This image, though, is the first image of a black hole that was ever produced by our same collaboration, but back in 2019. But this image is not of the black hole in the center of our Milky Way, but instead a galaxy 55 million light years away from Earth called M87. And you might think Sagittarius star and M87 look eerily similar, but actually that's no coincidence. This is actually predicted from Einstein's theory. But as I said, we published this image of Sagittarius star just 2 months ago, and the M87 image was published over 3 years ago. Yet these images were actually recovered from data that was collected in the exact same week of 2017. And so today I hope to not just answer how do we image Sagittarius star, but also what made it so much more challenging than imaging M87. And these lessons that we'll learn along the way will lead to 2 projects that I want to tell you about today on how in the future we may be able to tackle some of the challenges we currently have with black hole imaging by leveraging underlying structure in the data. And so my hope is that these projects and questions will motivate new directions in the neurosymbolic programming community, but I'd like to hear your ideas and stuff throughout the discussions as well. Okay, but before getting there, again, why is taking this black hole image so hard? Well, because this black hole, that ring that we saw, is so small, and we can only see it at a particular wavelength. Diffraction limits actually require that we build a telescope 13 million meters across in order to see that event horizon scale structure. 13 million meters is essentially the size of the Earth. And so although we couldn't build a single dish telescope the size of the Earth, instead the Event Horizon Telescope collaboration spent over a decade joining telescopes located around the world to build a computational telescope the size of the Earth that was capable of resolving structure on the scale of a black hole's event horizon for the first time. So how does this computational telescope work? Well, the EHT doesn't work, this EHT, the Event Horizon Telescope, doesn't work like a regular telescope. Instead, the radio telescopes here work in pairs, with each pair contributing a little bit of information to the entire image. So telescopes that are far apart can detect the smallest, sharpest features of the image. Orientation is also important, with each angle picking up different parts of the whole. And with enough samples, we can recover all those sharpest features. But in order to see the broader features, we actually need telescopes that are closer together. And so combined, these components of the image can provide a good representation of the image being observed. But making that perfect image would require that we have telescopes at all different orientations and separations. So we tile the entire globe with telescopes. But the EHT's 8 telescopes scattered around the globe only measure some of these possible pairings. Luckily, though, as the Earth rotates, the separation and orientation between the telescopes change, providing more, but not all of the information that we need to make a picture. So once we collect these measurements, how do we actually extract the image from them? Well, at this point, we have the data and we can kind of abstract away the astrophysics of the problem and think of it as just a purely mathematical inverse problem. We have the sparse data, and our challenge is to invert the measurements to find the image that caused it. And if we were given measurements that covered the entire measurement plane, this would be trivial. But since we only see a few samples, there are therefore an infinite number of possible images that are consistent with the data we measure. And on top of that, the fact that there's a different and quickly changing atmosphere above each of the telescopes across the globe also causes our data to be even more noisy, and the problem becomes even more ill-posed than just from the sparsity. So how do we deal with that? Well, of the images that are consistent with the measured data, there are some images that we consider more likely than others. So for instance, this image on the left, maybe we say, well, we would want something that is more compact than that, something that's smoother. And so we can, our goal then becomes to find an image that doesn't just fit the data, but is also likely under some sort of mathematical model of what defines a good or likely image. And so by injecting these preferences for image statistics into the pipeline, we use this additional information to whittle down from the infinite possibilities to maybe a single solution in this case that is a likely image that fits the data well. But actually, everything I've said so far, all these parts about the sparsity and everything there was also true for imaging M87, the black hole in M87. So then what makes Sagittarius star, the black hole in our own Milky Way, so much more challenging? Well, even though Einstein's theory of general relativity says all these black holes should act the same, from our perspective on Earth, these two black holes actually are very different beasts. So Sagittarius star is much closer to us. Don't be worried, still 27,000 light years from us, but it's much closer than M87's 55 million light years. And so that means that even though these two black holes appear about the same size in the sky, with Sagittarius star just a tad bit larger, if you actually factor in the distance to each of them, then the actual physical size of Sagittarius star is much, much smaller. So Sagittarius star takes up a physical size of smaller than Mercury's orbit around the sun, whereas M87's black hole size would extend past Pluto's orbit. And so it's much, much different sizes. And so remember though, I mentioned that surrounding these black holes is this hot gas spinning around. And that hot gas spiraling around these two black holes actually is moving at roughly the same speed. But where the gas takes days to weeks to orbit the larger M87, in the much smaller Sagittarius star, it actually completes an orbit in mere minutes. And that's just because it's a much smaller distance that it has to move around. And so here you can see videos of a simulation of Sagittarius star and the M87 black holes moving with the same clock we would see on Earth. And even though you might not be able to tell, the M87 movie is actually moving here. So why is this so challenging that we have this variability in Sagittarius star? Well, that means that as we are collecting data during the Earth's rotation, remember, we collect data as the Earth rotates and those projected separations, those baselines change, right? As we're doing that, the material is swirling around the black hole so quickly that Sagittarius star's appearance is changing from minute to minute. And so rather than all the measurements we take over a night being able to be captured by the same static image in the sky, as was the case for M87, now for Sagittarius star, every measurement we get from the telescopes is from a different snapshot of the black hole video that we're basically capturing. And so we can't simply just throw all these measurements into one pot and then expect them all to point to the exact same picture in the sky. And so now not only do we have to deal with sparsity and noise, but now our algorithm has to incorporate some way to deal with time variability. And each of these decisions that we make in this algorithm of not just like what is a good image structure, but also what is the variability that we want to account for, each of those decisions is going to bias our final picture. So how should we actually go about getting the range of Sagittarius star appearances where we're actually seeing the range of possibilities and not just one based upon some arbitrary decisions that we've made? So the way that we dealt with this is we developed 3 different imaging pipelines that had the goal of recovering an image from the sparse time varying data. And each of these pipelines has different hyperparameter knobs on them that control choices when solving for the best image. For instance, using the different image priors or different variability models. And typically these hyperparameters would be tuned by something like a human, but instead of having a human tune them, we instead wanted to search for the best set of hyperparameter settings to recover different source structures and then see how they influence the Sagittarius star images that we recovered. And in particular, we surveyed nearly 175,000 different parameters with these imaging pipelines and then saw how those imaging choices affected the images we got out. So for instance, we generated synthetic data as if the Event Horizon Telescope were actually seeing a disk on the sky that had no hole in the center, but had the input was still varying with similar statistical properties as the real Sagittarius star data. And then we found the best parameters to take the data of this time varying structure and find an image that represented the average structure that we saw in this data. So not a movie that we're recovering, but a single image. And once we found these best parameters to recover that disk shape, then we transfer them onto the real Sagittarius star data and to see what image that resulted in for Sagittarius star data. And we didn't just do this for the disk shape, but for a bunch of different geometric source structures that we thought could trick us up. And we didn't just find one parameter setting, but a range of parameter settings that worked well across different synthetic data sets. And once we had identified a collection of imaging parameters that performed well across all of the synthetic data that we had, so we, in that end, we whittled down from the 175,000 parameters to about 10,000 parameters. We then applied them onto the real Sagittarius star data to see the possible range of appearances that would come out depending on these different modeling choices. And so when we did this, we saw a huge collection of different images. So actually, each of these images is coming from the exact same data set. Each image here is actually consistent with the EHT data that we measure, but each one, as you can tell, is slightly different from one another. So in order to emphasize the common features appearing among most of the images, we then averaged them all together to get a picture that actually was the one that you've seen at the beginning of this presentation and kind of made the front pages of the papers and stuff. And here, this is just trying to show what is the common features among those images. And here, this bright ring pops out. But it's also important to note that not all the possible images looked alike. So in fact, we found that we could cluster the recovered images into 4 different categories based on similar visual features. 3 of these categories actually contained a ring-like feature with only differing brightness around the ring. However, there existed a much smaller 4th cluster that contained a variety of images that did not appear ring-like. How much smaller? Well, roughly 98% of the images that we created using this approach had a ring-like feature, while 2% were classified as non-ring. So the vast majority of the images contained a ring feature. And this, along with literally years of tests that I'm not going to be able to get into right now, led to the conclusion that although we can't say anything with conclusively, completely, that there is compelling evidence that the true structure of Sagittarius star is some ring shape, although the exact distribution of the light around that ring is a little unclear. But one question still remains in my head, and that's, should we kind of treat all of these images equally? So using simple data statistics, we didn't feel like of those 10,000 images that we created, that we could really cut any of those. But that didn't mean that maybe our data shouldn't be pointing us to preferring one of these images slightly over the other. And so that leads to some recent work that I want to discuss from my group on leveraging common structure for prior free image reconstruction. And jointly leading this work is a postdoc and an instructor here at Caltech, Oscar Leon, and my graduate student, Angela Gao. And the idea here is to, well, actually, let's first just step away from black hole imaging for a second and just think about the abstract problem of image reconstruction. So as we've talked about so far in image reconstruction problems, the goal is to recover a clean image, which we're going to call X here, right, from a noisy, corrupted version of that image Y, where X is degraded via some known forward model. So for instance, bringing it back to the black hole, like X might be our true underlying image of the black hole, and Y are our telescope measurements or something. And in many problems, including the black hole imaging problem, as you've seen, this problem is highly ill-posed. So we have to use priors or regularizers in order to recover that image back. But as we just discussed, these priors can exhibit bias and human bias, either in designing them initially or selecting which ones to survey in our pipelines, right? So the first question we aimed to answer was, given only the noisy corrupted measurements and a set of possible image priors, are we able to select the best prior for reconstruction or try to rank them in some sort of way? And so what do I mean by that exactly? By just looking at the data here and not knowing anything about the underlying image structure, I want to be able to select the prior that I should use in solving the inverse problem. So for instance, let's say I was given 4 different prior models, image priors. So one that characterizes images of zeros, another one that characterizes images of 1s, 2s, and 3s. So I have 4 models that I can choose from, but I only see this data Y. I don't know what the true underlying source looks like. And by just looking at that data Y, I want to be able to figure out which of these 4 models to use for the image reconstruction task. A natural approach would be to find or select the model M that maximizes the model posterior distribution, the probability of model M given our data Y. And that is conditioned on the noisy measurements and find the model of highest likelihood. Unfortunately, though, so you can write this, using Bayes' rule, and if we don't have any preference for any particular model, then it reduces down to solving for the probability of the Y given M, right? But unfortunately, computing the probability of Y given M is intractable. But in our work, we showed how it can actually be well approximated using the evidence lower bound, or otherwise called the elbow. And in particular, although I don't have the time to get into exactly how this is derived, we realized that if we train a variational distribution to well approximate a posterior distribution of the underlying images X given data and a model M, then we can compute the evidence lower bound or elbow of this variational distribution. And if that variational distribution, if we believe it well approximates the true posterior, then it can actually be used as a proxy for the probability of the model given the data Y. So for example, using this elbow as a criteria for selection, we're able to determine by only looking at this noisy data Y and not knowing anything about the structure of the underlying images ahead of time, that of these 4 models, the model for 3s is the one that has most evidence for us to use. So I'll just give a little, so each term in this elbow objective encourages certain kind of properties of our model. In particular, the first term requires that our model should lead to an estimate of the image that is consistent with our measurements. The second term encourages samples, image samples that have high likelihood under our image prior. And the final term, and probably most important term, encourages a model that leads to fatter minima that are less sensitive to small changes in the estimated image. So this is actually distinctly different than just saying, okay, I'm going to solve the inverse problem under each of these models and find which one has the best map or something like that, because here we have this entropy term, and that entropy term encourages these fat minima and actually makes quite a big difference where you don't get just stuck in some weird corner cases. So to help demonstrate how this performs, let's take a look at this simple example. So here we have a noisy image of a 2 in the second column here. But let's say we don't actually know it's a 2. All we see are these noisy measurements Y. And what we want to do is we want to denoise that image with various different image priors. So ones that prefer 0s, 1s, 2s, 3s, all the way to 9s. And you can see in the top, that's the mean of the posterior distribution. So it's kind of like the denoising result under different image priors. And you can see that it's kind of chosen, for instance, for the priors of 0s, you can see that it kind of matches where we have information in the actual noisy image we've observed. So you can see the left side is brighter than the right side, and maybe that is a fairly good fitting 0. But what can we actually say? Can we actually determine which of these priors is actually better by just looking at that data Y? And it turns out that by using this elbow that I mentioned, it actually selects the model for 2s. It has having the most evidence from the noisy data. And in this case, we know that because we generated the data that it's actually from a 2, and it makes sense that that's the best model. So that's perfect. So here the elbow actually worked really well. But here's a case that highlights that this idea, isn't perfect. So here is a noisy image of a 3. And so again, we reconstruct with each of these prior models and compute the elbow. And when we do that, we see, in fact, the 8 has the lowest negative elbow. So just eking past the elbow for the 3 model. But if you actually look at the 8 reconstruction, you'll see from the noisy measurements that it actually is pretty reasonable. And if I just saw this noisy image, I probably wouldn't be able to tell you if it was a 3 or an 8. In both of these models models scored comparably. And so you could say, well, even though it might not give you the exact right prior model, it gives you some sort of ranking, at least, of how good these different prior models should do in doing this reconstruction of this ill-posed inverse problem. So yeah, although it might not be perfect, it can tell you at least how much evidence there is for these models to use in reconstruction. So getting back to the black hole problem, perhaps rather than blindly just applying different priors and then seeing how they perform on synthetic data only, perhaps we can have the data help us tell the story of which of these models actually is most appropriate. Or we could even potentially weight each of our solutions by the evidence for each of these priors in our data. But here we're asking if we can select among a discrete number of prior models. So maybe we could even push this idea further. For instance, could we just solve the inverse problem without any predefined image priors at all? And it turns out we can in some cases. The key insight being that common structure across independent problems is sufficient for regularization alone. And so what do I mean by that? Well, going back to the black hole problem as an example, remember that our black holes are evolving over time. So Sagittarius star is much faster than M87, but both of them are evolving. And so thus far, all the reconstructions I've showed you have been using these hand-designed priors, a large collection of them, but they were still hand-designed. And so in this work, we asked the question, well, can we use just multiple observations of the black hole over time as regularization alone? So we don't know what the black hole looks like really ahead of time, but instead we have these multiple noisy observations of the same black hole, but as it's evolving over time, and we're going to represent it by these messy images to the right. And at each point in time, we collect these messy measurements of very similar looking black hole images, and we trust that the underlying images should be similar because they are all of the same object. They've just changed slightly over time. And so we leverage this knowledge that all the measurements should share some similar looking underlying images. And so to solve the inverse problem without a predefined prior, the way we do this is by learning a generative neural network that takes low dimensional input and maps it to images that well fit the posterior distribution for each of the measurements we've collected. So in other words, we basically find a low dimensional manifold that can reproduce the images from each of the different independent measurements we've made over time. And we do that by simply optimizing with a proxy to the elbow criteria that I just discussed earlier for the model selection. And so by simply solving the inverse problem simultaneously for all these measurements we've collected and forcing them to all use the exact same generative model, we've been able to show, at least on toy problems of black hole reconstruction, that we can reconstruct cleaned up black hole reconstructions when we only have access to the noisy measurements. Again, the key insight being that these underlying images share common structure, and it tries to find the simplest collection of images that would explain all the measurements we've seen. So even though we've only applied this in the simple setup so far, we're working on applying it in more realistic settings. And I'm just super excited for the potential of what it can achieve if we can move past just using hand-designed priors and just using much weaker kind of regularization, just the idea that there is shared common structure over time as our regularization alone. But here we've gotten pretty far by just assuming some underlying structure in the data, but all of that shared structure, but all of the images actually, they all live in this low dimensional space. But if we had additional structure, I'm sure we could do a lot more. So a question I have for the neurosymbolic programming community is, can we learn what structures are in that data? So for example, if we had a dictionary of possible structures, and if we could then take this dictionary and learn from it which ones fit the data that we observe from different observations, perhaps we could use that, for instance, a set of transformations or something, to help us better regularize our problem, even though the regularization is not directly in the image domain. Anyway, it's just an idea, but I'd like to hear your thoughts later. But for now, let's just get back to the story of the Sagittarius star black hole. So this image was this great validation of what we expected from general relativity. But even further than just testing general relativity, we find that by comparing this picture to simulations scientists have made for years, the image that we took is actually incredibly consistent with a number of these predictions. But there also were some surprises. So black hole simulations like the one I'm showing here have incorporated all the physics that we believe is going on around a black hole. And these simulations have been so important because they drive a lot of our understanding of the astrophysics around the black hole so far. But all these simulations depend on a huge number of possible initial conditions and simulation choices. So rather than just simulate one video, the EHT decided to make this huge collection of simulations of black holes with many different conditions. So making up around 1.8 million simulated black hole frames. And we learned a lot by just studying these simulations and comparing our recovered black hole images to them. So for example, by comparing these videos to constraints that are imposed by both our images of Sagittarius star that we reconstructed, as well as other measurements from other wavelengths, we can play basically this cosmic game of guess who and cut out different simulations with conditions that lead to images that don't match what we actually see in our data. And when we do this, we were actually left with basically just two models that are most likely to pass all our tests. And that already tells us a huge amount of information, like the fact that the black hole is most likely facing more towards us than we originally expected. But before you get too excited about what these simulations are actually able to predict in terms of the underlying black hole parameters, I want to let you know that getting this result, we actually left out one constraint: the amplitude of Sagittarius star's time variability that we observed. And that's because when we add that constraint, actually none of the models actually passed our test. We found that the models that the computational astrophysicists have developed way overpredicted the amount of variability and that would be in our data. In fact, our black hole, the Sagittarius star black hole, was a lot quieter than we expected. It was still evolving for sure, but with not as much turbulence as our simulations had predicted. So although our image is this fantastic validation of what we expected from general relativity, when it comes to astrophysics, our current models predict too much variability, and that was surprising, meaning that there is still some physics that we need to put into our simulations to get it right that we don't know about. And so to better understand this black hole evolution, we'd love to recover this evolving structure. So the next question on all our minds was, can we recover the dynamics around the black hole? So how might we actually do that? Well, remember the data used to recover the black hole image has to actually be taken over the course of a night. As the Earth is rotating, we collect different measurements that together were used to make the Sagittarius star image. So could we use this collection of different snapshot measurements to bake a black hole movie? Well, what we could do is we could break the data into chunks corresponding to different times and try to make an image from each chunk of data. In essence, reconstruct each frame of this black hole movie independently. But this would leave us with far too little data to produce high quality images. And so instead, what we've done is develop methods to reconstruct full movies of the black hole evolving over time. But if you thought recovering a static image was a Hardell-Post problem, then this ends up being orders of magnitude more challenging because we have the same amount of data, but now we have to solve for all the pixels in a full movie rather than just a single frame. And so to get around this, we include temporal regularization, where the temporal regularization controls the continuity that we impose from frame to frame. And we can crank up and down that continuity we impose so that we can find movies that fit the data, but allow for more variation from frame to frame or less variation. So now with this method in hand, we went to go reconstruct our actual real Sagittarius star data. But when we did this, we found that the movies that we recovered actually depended on how much we cranked that continuity term sometimes. So when we give the movie more flexibility to fit the data, when we crank that temporal regularization down, we often recovered a shift in the position angle over time. But this effect would actually disappear if we enforce the temporal continuity even stronger. And it was too difficult to say by just the amount of signal to noise ratio in our data, if that really ruled out that really strong continuity. So these results show that while the image of Sagittarius star likely exhibits interesting and measurable dynamics, our current methods weren't able to conclusively determine the exact position angle of the bright spots around the ring over time. And so as important as it is to continue pushing on the algorithmic approaches like this to squeeze more out of our data, it's also important to realize that to extract more science, we also have to think about improving not just our algorithms that analyze data, but also our instrument that collects the data to begin with. And to that end, we've been working on improving the actual Event Horizon Telescope network. So in 2017, we observed with telescopes at 6 different locations. And then since then, we've been building out our array to get more data, adding telescopes in Greenland, France, Arizona. And the one I'm clearly most excited about is we're adding one here at Caltech as well. But imagine what we could do if we actually added 10 more. Well, maybe we could actually make a video of the gas falling into the black hole in the center of our galaxy. And being able to make a video like this would be a huge scientific goldmine. But perhaps if our goal is to better understand that missing physics that we're after in our astrophysics models of turbulence, there's maybe another approach we should take apart from just simply video reconstruction. So here I am showing the spectrum of possible motion recovery algorithms. On one end is recovering a non-parametric flow field, which would be like doing a video reconstruction and then doing something like optical flow that tracks the motion over time of that video. And this is maximally flexible in what we can recover, but in the end, it's not necessarily very interpretable. And on the other end of the spectrum is estimating parameters of a physics-based black hole model. And while this result is maximally interpretable, this approach has the disadvantage that we're tied to a black hole model that we already know is not correct, right? It's overly restrictive. And so rather than picking one of these extreme options, we'd like to find a middle ground. Use a model that balances the pros and cons of these different approaches. And towards that end, we've been working on modeling the persistent evolution of black hole sources as the result of an advection diffusion process and solving for the parameters of this model that best fit the observed measurements. And so this intermediate option tries to find an interpretable compression of the motion field by asking us to only match the persistent motion statistics. We're not recovering every pixel over time, but instead the statistics of the motion. And this work is led by Aviad Levis, who is a postdoc in my group, but also with collaborators in black hole physics, David and Charles here, as well as Joel Trop, who's at Caltech. And so let's dive in to understand a little bit better. So here I'm showing the equation of a stochastic partial differential equation, a PDE, describing an advection diffusion process. And don't worry about the math, don't worry about it, I'll just point out the relevant components here. So in this process, there are 2 parameters we really care about, V and D, where V is the velocity field that describes how the bulk is moving, and D is the diffusion field, which describes how material spreads out in space. So for instance, these 2 cups contain water with different non-isotropic diffusion fields, resulting in dye spreading out differently in them. So therefore, you might imagine describing the motion of the dye using a PDE like this with different underlying parameters D. And in this work, we use a black hole motivated fluid model to parameterize each of the fields with 1 parameter each, theta 1 and theta 2. And by solving this equation for rho, we can obtain movies that obey this advection diffusion process under different parameter settings. For instance, for this particular choice of theta 1 and theta 2, whatever random noise we input as our forcing function, we're always going to get some sort of like swirling structure in the end. And by tuning these parameters appropriately, you can see that we can produce flow fields with this model that, when paired with a jointly learned envelope, mimic that of the smoothly evolving black hole simulations. Okay, so that sounds great. Our goal is to find the parameters theta here that best describe our observed source motion. However, there's a catch. And that's that this is a stochastic partial differential equation, meaning that the fluid flow movie that we get is dependent on that input forcing term epsilon. And therefore, two random fields with the same underlying velocity and diffusion parameters result in very different pixel values over time. And therefore, a key challenge to estimating the dynamics is that the pixel values are driven by this unknown random source, which we do not want to estimate. So an insight of our work that unfortunately I don't have time to get into much now, but is that by using dimensionality reduction, we can ignore that epsilon term altogether when determining the parameters that best fit the dynamics. And even with measurements from a sparse telescope array, we can begin to recover some properties of the dynamics decently, like the direction of the fluid flow. But this becomes even much better when we simulate measurements coverage that would be for a futuristic telescope array that we're interested in building. And so in this case, not only can we get the general rotation of motion, but also important information about the wispy structure coming off the black hole shadow. And obviously what we've recovered here is not a real model of black hole physics, right? It's simply a surrogate model that mimics the black hole evolution. But the advantage is that this approach we can extract is still interpretable while still being flexible to see something a bit surprising. But although we claim this model is flexible, it can still be restrictive in a lot of cases. It currently doesn't have enough flexibility to really describe all the different physics we're most interested in targeting. And so my question, or perhaps even charge to this community, is can we learn directly from the data which physics models best describe the data we observe? So rather than just fitting to a pre-described model, can we first figure out which physics models we should even be considering and then fit to that? Or perhaps even find a residual model to add onto the incomplete black hole models that we currently have. And I'm sure you have a lot of great ideas, better than me for this, but perhaps even bringing over ideas from the prior free reconstruction may be a starting point. So after all that work was about taking the data directly and trying to learn which models best fit that data. So maybe in the future, these two general ideas could work together to synergistically not just make better images or movies of a black hole, but actually discover new physics. So to close, it's clear we've learned a lot from the images of Sagittarius Star already, but this is really just at the beginning. There's still so much more to come, and hopefully one day we'll not be able to show you a static image of a black hole or a movie, but with the help of computational methods, actually use the dynamics we recovered to build up a new understanding of the astrophysics mechanisms around black holes as well. And so with that, I want to thank the amazing team of EHT collaborators that worked tirelessly on these results over the last few years. And in particular, I want to highlight Oscar, Angela, and Avia, who led the additional projects that I talked about today. So thank you, and I'm happy to take any questions.
Questions?
Hi, this may be a question on a left field, but are you familiar with Wolfram's physics project?
No. Yeah, maybe you can tell me a little bit about it later. I don't know, or now.
Oh, sure. The super abridged version is that he's trying to derive all of the laws of physics computationally.
Oh, okay.
And then do a search through computational space to figure out things we don't know.
Yeah, so I know of a few people who work in this general area. A couple of people like Steve Breton, who's here, Miles Kramer, who I've heard a little bit about, and Chuda Kandambi, but I'm sure there's many people. But there's just this idea of taking the data and trying to learn physics equations. I think it's just really, really cool. So yeah.
Thanks.
Thank you so much for the talk. So coming from actually the robotic side, less the neurosymbolic, there's for us often debugging means that they're running it, you have to run it, we're just running the real robot, and it's the only way to really find where the issue is.
Mm-hmm.
Have there been, beyond just these amazing images, have there been lessons learned from being able to actually visualize the black hole and visualize the stuff beyond just what was predicted or what you could do in simulation? And what have been some of those lessons that come from it?
Well, the process of actually making the image was, we learned a lot and we had to modify our methods a lot to deal with the challenges of the data. And that's part of the reason I didn't get into it all, but that's why, you know, the Sagittarius star data took so much longer than M87, because the M87 more aligned with what we kind of previously thought, you know, we'd have to deal with. Of course, we knew that there would be time variability, but we didn't realize how challenging it would kind of be. But I would say, like, apart from that, just the fact, I think the biggest, and there's obviously surprises along the way, but the biggest surprise to me is that our physics models of the astrophysics don't currently describe the data, at least in the variability. And so that's something that we didn't, you know, we didn't at all predict before actually seeing the data. So I'm not sure if that answered your question, but I think there are both, there were both surprises and lessons learned on the computational side, on the reconstruction side, but also on the physics side.
I'm wondering, you mentioned that the predictions by the simulation of the astrophysicists.
Of what, sorry?
The predictions of the simulations of
Mhm.
the astrophysicists.
Yes.
They had higher variability in the predictions than what you observed from the actual black hole.
Yeah.
I'm wondering, what was the basically difference there? Was it like tens of percentage points or orders of magnitude difference in prediction?
Oh, it was at most, I would say, order of magnitude, but and it's also not on the turbulence itself, it's on the amplitude of the turbulence. So you would have these wild like changes in the brightness of, you'd have these flares that would come up and stuff like that. And what we saw is a little more like burbling rather than these wild like changes and stuff like this.
Well, and you commented that this might mean that there might be basically issues in the theory that they used about black holes.
Yeah.
So that's
Yeah. I'm not on that side of things, but it's definitely something that would be interesting to, yeah, I mean, and there are some things that are probably approximated just for computational reasons. I mean, making a single one of those models takes millions of core hours to compute. So they're very computationally intensive. So, you know, I'm sure there is a little bit of physics that they know about that they haven't included yet, but actually like the colleagues that I work with have said they don't think it's just anything that they've already know about. I think that there are still work to be done there. Yeah.
Hi, I'm curious if there are other astronomic phenomena which we can observe, but we know even less about, or have even fewer theories about the physical models, where, for instance, you know, here is a very important part, was we had simulations for a long time of predict the behavior of black holes and compare that against images or use it to generate the images. But are there things we can, to some extent, see but have no idea, for instance, or have very few ideas about the actual forces of physics that are driving them?
Oh yeah, well, I mean, I don't know about physics because, but in terms of astrophysics, I think there are a lot of things. And the first thing that comes to mind, although I'm sure there's lots of this, what are these called? Fast radio bursts, which I think in the last couple of years we've learned a lot more about. But like, I think even when I started at Caltech, the saying was there were more theories of what they were than observations of them. So I think that there, you know, a lot of times these are discovered accidentally, things like this. And then afterwards, then people try to come up with theories and everything. But in terms of the fundamental physics, I mean, general relativity has been pretty robust, you know, across a number of different experiments. And we haven't found, there hasn't been yet an experiment that has really broken it, although we know it, you know, there should be a breaking point at some point. But like, but in terms of the astrophysics, there's a lot, I think, that people are still learning and trying to understand.
Hi, so first of all, thanks for the great talk. So in the middle, you raised this issue about the variability that was surprising, and at least the way it sounded is like some of the work that you were talking about at the end was hoping to get better models to see if we could better understand what the problems here might be. So I was just wondering, so you kind of talked about one approach, but what were the limitations of that approach that prevented you from, or did it provide any insight, or if not?
This last approach that I talked about with the,
yeah.
so, yeah. So we're in the process of applying. I mean, when you work on these big collaboration projects, it's kind of like a slow moving train. So this was work that we published at the end of last year. And so it was a little bit late for us to try to incorporate this into the work that we published just 2 months ago. But it is something that we're interested in. But I also think it's still not ready really to use. I mean, the real data is really messy. And so you have to, whenever we use these kind of methods on the real data, we go through like many tests, rigorous testing on many synthetic data. You know, it takes a long time before we feel confident that we'll actually work on the real data. And we don't want to jump to conclusions too much and then try to interpret too much. So I think we're still at the beginning stages of that, although we're working on it to try to see how it works and try to build it up and become more robust to the problems we have. And I really actually think that this thing about having these different models is going to eventually be essential, because right now we're just working with one model, but you know, there can be some craziness that maybe goes outside of the range of that model can handle. And then we want to be able to say that we at least know that model doesn't fit the data. And right now that's a challenge. So yeah, but good question.
Thank you.
I'm wondering, looking in the future, scaling this up to maybe observing or videos of many black holes. Like, for example, when do you think we will have, you know, basically real-time videos of, let's say, 10 black holes?
Yeah, so this is there's multiple parts to this question. So actually, the M87 and Sagittarius star black hole are the only 2 black holes that we know that are large enough on our sky to be able to see with an Earth-sized telescope. So if we want to see other black holes, we'd actually have to go larger than an Earth-sized telescope. We'd have to put telescopes in space. And so that's something that we're interested in, actually, that we've had a workshop here at the KISS Center for, and that there is some interest in, but doing that would be very costly, and so you have to have a real motivation to do that. But it is something that is interested. So I would say it's, you know, we look at other black holes, but we're not seeing that ring structure. So just the Sagittarius star and M87, but if we go to space, then we can start seeing more and more. But then yeah, and then as far as like real-time movies, I mean, I think for Sagittarius star, once we start putting these telescopes down, we should be able to get movies. So I think there are different predictions of how long that would be and how much data we have to try it out and stuff. I mean, we even made movies already. It's just a question of how much do you believe those movies, right? So, but I think like in 10 years or so, we should have enough data to actually make a real robust movie that we really, really trust.
Hi, thank you for your presentation. I was curious, I know little about telescopes, but there is new one, James Webb telescope. Could you combine data from that telescope and like increase number of samples you have, I guess?
Yeah, good question. I mean, so the James Webb telescope, really exciting with the new images coming out and everything, but it's a very different kind of telescope. So here we work, if you wanted to I think that there is complementary information that we might learn about our universe and stuff, but as far as incorporating it into this telescope, this virtual telescope, unfortunately, we wouldn't be able to do it because for 2 reasons. One, that it works at a different wavelength of light. So we have to, there's only a certain wavelength that will like pierce through everything and get to that ring structure. And so we have to use these radio wavelengths. And 2 is that we actually have to have these atomic clocks at every location, and we do synchronous observations and stuff. So the James Webb just doesn't have that kind of technology on it. But that's not to say that you couldn't put a space telescope. The technology is not there yet, but it definitely to put that atomic clock and everything like that. But you know, from conversations with people at JPL, it's definitely possible in the next 5 to 10 years or so. So even though James Webb is not likely to work with us, I mean, there's complementary information that we could get from there, and maybe we could go to do another space mission.
So just claiming that I don't know anything about the domain, abstractly, right? Were there instances where you realized that you had to, that informed what kind of data you wanted to collect to better your models, like depending on what part of the model you were unsure about? Were you able to conclude that you had to collect a specific kind of data more?
Yeah, it's a great question. So one direction of our work, maybe this is not exactly what you're thinking, but it leads me, the first thing I think of is one thing that we've been working on in our group is not just working with wherever they were putting telescopes down, but actually deciding where should we put those future telescopes. So I said, the goal is to put 10 more telescopes around the globe. But where should we put those? There are maybe 50 possible options where to put those 10 telescopes at the high mountaintops and stuff. And so one thing that we're working on is where will we get our biggest bang for our buck? And we've been working on some so this is like a combinatoric optimization problem and everything, but we approximate it with some differentiable kind of learning, and we can try to identify for different tasks, for instance, image reconstruction or video reconstruction or model fitting or something, where would the best telescopes be? And depending on your task, it will slightly change the results that you get. This is something that we're actually actively working with this next generation telescope array to decide how to whittle down from those 50 possibilities to 10 that we want to propose.
So I'm wondering if you can comment a little bit on the trade-off between more data and algorithmic complexity. So it seems to me, and correct me if I'm wrong, that if we build more and more telescopes, we will get essentially a better picture. Do you have any thoughts on whether we should invest time and energy on better algorithms or more data?
So first of all, I don't know where you are, but I'll just talk generally to the room. Okay, over here. Great question. I think we need both sides, and I think we need to optimize them jointly as well. Typically, these ideas are kind of optimized. First, you optimize your sensor array, or your sensor, like your telescopes, and then you decide how you're going to interpret the data and deal with all the problems that you caused by not completely understanding the problem. And so I think that in the future, we really should be thinking more about jointly optimizing these two parts. And I think that you can't just focus your energy on just one or the other. I think we need to improve both our algorithms and our measurements to get really to the next level of what we can do with what we can do here. But you can squeeze a lot. I mean, a lot of the things that we did here, you wouldn't have been able to do with the traditional methods that have been around in radio interferometry. We had to develop new methods to get that far. And I'm sure that there are much better methods than we've developed. And so I think you can squeeze more, but eventually you're going to have to collect more data. I also want to highlight that usually we think about going to our science friends and tell us what problems that we should be working on. Throw me a problem and then I'll work on the algorithmic component of it. But really what I find working in this collaboration is that sometimes actually the algorithmic advances that we make actually motivate new science. So this idea of video reconstruction, we actually worked on originally back in 2017 or so. And this kind of excited the community, and people weren't really thinking about black hole video reconstruction at the time. But because of that, they realized, we can get so much more out of the data. And it started this now over 100 people team that is interested in putting these telescopes around the globe for the purpose of getting videos. And so I think it's also interesting to not just wait for the scientists to give you problems, but go to the scientists with different, computational tools and say, hey, does this open up new possibilities too? So yeah, I think I'm really excited about that actually.
Hi, Katie. Thanks for the great talk. I'm curious if you thought about imaging objects that have a gravitational lens between us and the object, and if that would increase the difficulty of the inverse problem, or how would you tackle it?
Yeah. So for this black hole imaging project, I mean, I don't know what we can do, but actually another one of my students is working on starting to work on doing dark matter reconstruction by looking at the lensing of galaxies. And so looking at slight kind of shearing and stuff across collections of galaxies in some field to try to recover what was the distribution of dark matter that led to that lensing. And so this is also a really interesting ill-posed inverse problem. So at its core, they're all these problems are very, very similar. But in terms of using the lensing for this problem, I'm not sure. I guess I'd have to think about it, but there are a lot of cool problems around lensing. So this is strong lensing, but that'd be weak lensing kind of, but similar ideas, yeah.
Okay, thank you.
All right, so I think with that, let's thank the speaker again.